That's true.
Whatever you want.
I also want to finish it by tonight.
2020 or
2030. No, 2020 is going to take some time.
2030. I think I'm done with like parts A and C of number 2. We got the same thing for number 1. We didn't get the information.
I have an regulatory now.
Yeah, the 6P over ML. Mark the 6P.
Oh, it's all I need.
6P over ML, right?
I don't remember exactly.
Wait. For number 1. XP over ML.
Look at the rest of it.
6P over ML.
Oh,
2030.
But then I'll
Number 1, the angular exponential. What do you number 1 and 2?
Yeah, but he really.
Oh, so you did the other question? How did you get it? It's 1 over 12.
Oh, I did it by
Oh. Huh.
I did it also do it. So I don't know.
Wait, so you did 3.5?
Okay, good morning everyone. So I have posted the pre-lecture slides. They are available in the PDF and the note format. If you'd like to go to Carmen, download those, and follow along with what I'm doing in class. Okay? Alright, so this is the last problem on combined loading. And then I'm going to move on to principal stresses, plane stress analysis, and so on. So in this problem, you're going to have a pipe which is in the form of an L shape. Okay? I'm going to draw the figure. You already have it on your PDF if you have it open. Alright, and then we have the following forces acting on it, and I have the axis system as well in the manner shown. Alright, so the back end of this is fixed, as you can see. And the following are the axes, x-axis, y-axis, and then if I use the right-hand rule, the z-axis is drawn in the third direction shown. So this is the z direction. Then I have the following distances. This is an elbow joint, essentially. I have the length and the width of this elbow joint as 1 meter and 2 meter respectively. So, there are some forces acting on it in the following. Okay, so the forces are of magnitudes 200, 300 and 400 newtons. Space. And the distances are as shown. So along the z-axis the distance is 1 meter, and along the x-axis the distance of the elbow is 2 meters. So starting from here. Two meters, and then I have a 1 meter distance. Alright, is the figure clear for everybody? On the fixed end, I am asked to find out the state of stress at a point A. Which obviously means I have to first find the support reactions, I have to find the reaction moments, and then decide what are these that are going to contribute to the stresses at the point A. Okay? So obtain state of stress at the point. And we can choose to do this at different other points as well, but I want to take this one particular point, complete it properly by the end of class today. First things first is we have to draw the free body diagram. And to draw the free body diagram, usually if I have a three-dimensional problem, I draw what is called as a line sketch, which means I don't draw the entire 3D problem per se, but I just draw the points of interest for me and I join them together. So this is what I mean by a line sketch. I'm going to draw it on this particular panel here. Okay. So first I draw the elbow joint L shape. And then on the side that is closest to us, I'm going to draw the forces acting, 200, 300 and 400. Then I set up the axes. I'm looking at the centroid. So I'll call this as point C. Okay, C is the centroid of the cross section. Let's say that the radius of this pipe elbow joint is 20 millimeters. So radius R is 20 mm. And let's say this is a solid section, okay, as you can see. And here is point C. And I first set up my axes, X, Y, and Z. This is the point, see? And then I draw all my reaction forces, all my reaction moments by assuming them to be in the positive coordinate sense. I'm going to have positive forces in the x direction, y direction and z direction. The force along the x direction is going to be a normal force because it is normal to the cross section at the fixed end of the pipe. Okay, so the x-axis is normal to the pipe cross section, so I'm going to call that force, I'm sorry, this is the force Nx, not dx. Normal force, then shear forces along y and z, as usual. Vy, Vz. In most problems, you will not be given the coordinate axis, but for this particular semester, I will decide to give the coordinate directions or the coordinate axis for each problem we solve. Okay, if it is in an exam or in any other situation. Then I will choose to draw the reaction moments at the fixed end of the pipe. I'm going to have three. One is along the x-axis, which will be called the torque. The double arrows depict the direction of the torque. The curly arrow depicts the sense of the torque. And typically when you draw it, your double arrows will be pointing towards the positive directions. This is going to be Tx. Then I'm going to have something in the My and the Mz directions. This is My. And then one more in the Z direction. Mz. And it is important to understand that if I extend the line of action of this force of 300 newtons, it is going to intersect the z-axis. As if I extend this line here, extend this guy, they are all on the same plane. Does this same make sense to everybody? Do you see the figure? Okay, they are lying on the same plane. Okay? Essentially, I'm looking at this plane here. This is the plane I'm envisioning there as I'm drawing it out. Alright, distances 1 meter and 2 meters. So this is 2 meters. This is 1 meter. And if you want, you can call this point B. And so which is this point. Any questions so far, please? Okay. Sum of forces in the x, y, and z directions will give me the reaction forces. Sum of moments at the point C about the respective axes will give me the reaction moments as well. Two of them will be the bending moments, there will be a torque. Okay? So force balance. Forces in the x direction, positive x direction being positive. I'm going to have 300 newtons, I'm going to have nx, so nx is minus 300. Along the y and the z directions likewise. Sum of forces in the y direction, forces being 200 newtons pointing along positive y, the shear force Vy along positive y, so Vy is minus 200. And the last one, along the z direction, I'm going to stick it up in here. (400 newtons along the positive z, Vz along the positive z, so Vz is minus 400. All right, any questions so far? All of us on the same page? Okay. When I do the sum of the moments, I will be a little more careful. You don't need to keep drawing all these figures again and again. I just do it for simplicity. Okay, just the figures that you have in your iPad is sufficient. I'm going to start summing moments about the x-axis. I'm going to draw my L shape once again, and then mark all the forces that are relevant to me. Sum of moments at the point C in the x direction is 0. Okay, all the moments that are pointing along the positive x-axis will be taken as positive. This is my positive sign convention. I draw the L shape. I have the moment about the x-axis, so x, y, and z first of all situated here. This is Tx, okay? So I have Tx as a positive value first snuck in here. So Tx. Then I have three forces that I'm going to be drawing, 200, 300, and 400. All right, then x, y, and z. This is the y-axis, z-axis, this is the x-axis. Then I start whittling them down one by one. If I have a force parallel to the x-axis, it is not going to contribute to any moments about the x-axis. Okay? If I have a force that is intersecting an axis, then that force will also not cause a rotation about that particular axis. So if I look at the 300 Newton force, its line of action is intersecting the x-axis, which means that is not going to cause a rotation. So this is not going to be contributing. So the only force I'm left with is a force in the y direction. There is a perpendicular distance for that force from the x-axis This is the x-axis. And the perpendicular distance is 1 meter, as we have seen in that figure there. And if I use the right hand rule, fingers of my right hand aligned with the force, my palm faces the x-axis, I roll my fingers, my thumb is pointed along the negative x direction, which means that this force is causing a rotation about the negative x-axis. Once again, fingers of my right hand aligned with the force, my palm is facing the axis of interest, which is the x-axis. This is all static stuff. I roll my fingers, pointing along the negative x-axis. Okay, so if I want to draw it out, this is 200 times 1, so it becomes minus 200 up there. Newton meters. Okay, so that's actually 200 times 1. So I want to make sure that's not a force but a moment. I will do the same thing for the y and the z moments, and then we will go back to the cross section where the point A is situated. We will draw all these reaction forces and moments. Okay, sum of moments about the point C along the y-axis. Is 0. This is my positive sign convention. Every moment that causes a rotation about the positive y-axis is treated as a positive moment. I draw my line sketch. X-axis, y-axis, and z-axis. About the x-axis, I have my reaction moment my. About the y-axis, my, positive. Okay. Once again, the way I have drawn it is, if I take the fingers of my right hand and I clutch this vertical line, my thumb is pointing along the positive y direction. The direction that my thumb is pointing is representing the double arrows. The sense that my fingers are curling represents the curl of this arrow. Then I draw the forces at the point B. Okay, so these are my forces. 200. 300. I'm sorry, this is 300, right? I think I flipped it. It's supposed to be the opposite. That's 400. I'm sorry. Not that it made a difference to us here. This is 400 and 300. First thing I put is my. My is positive. Then I start whittling down what are the forces that are of not much consequence to me. If I have a force parallel to an axis, that is the first creature I'm going to strike down. So that does not make a difference for me. Okay? Then, this force, if I look at its line of action, is not intersecting the line of action of the y-axis, right? Because the line of action of the y-axis is this vertical line. If I take this 400 Newton force, it is not intersecting the y-axis, the line of action. And typically what you can do is, according to the principle of transmissibility, you can start moving forces along their line of action. Which means this 400 Newton force, I can actually say is acting here, because I can just transfer it along its line of action, just sliding things. I'm not changing its magnitude, I'm not changing its direction as well. Okay? Then it is quite clear to see that if I take this 400 Newton force, I have a perpendicular distance all the way to this y-axis here, and so if I use the fingers of my right hand, my fingers align with the 400 Newton force, my palm faces the y-axis, I curl my fingers, it is going to cause a rotation in the positive y direction. Does this make sense to everybody? Once again, if I have a force, I can slide that force along its line of action without any loss of generality. I am not changing its magnitude, I am not changing its direction, I am just changing its position in space. When I do that, I immediately recognize, okay, if this is the y-axis here, this force has a perpendicular distance with respect to the y-axis, the distance being 2 meters. And if I use the right hand rule, fingers of my right hand aligned with the force, my palm is facing the y-axis, I curl my fingers, my thumb is pointing along the positive y direction. Okay, so this is going to cause a rotation 400 times 2, so I'm going to add that in here. Taking care of this guy. The last one left is the 300 Newton force. And it's quite evident seeing here that this is a perpendicular distance of 1 meter all the way to the y-axis. And if I use the fingers of my right hand, align it to the 300 Newton force, my palm is facing the y direction, I curl my fingers, it is pointing along the positive y direction. 300 times 1. Does this make sense to everybody? Once again, you can use the principle of transmissibility, but it is not of much use because I could take this guy and I could move that here. But then if I do that, its line of action is going to intersect the y-axis, so that is not of much help to me. It would have been helpful to me to do it for this force because it is just a tool of visualization. So I keep this force where it is, and I see that if I take this force, it is trying to rotate in a counterclockwise sense about the y direction. Right hand rule, fingers of my right hand aligned with that force. My palm is facing the y direction. Curl my fingers. My thumb is pointed about the positive y-axis. Okay, so there is one more rotation here. 300 times 1. So plus 300 times 1 is equal to 0, or if I solve for my, that's 800 plus 300, negative 1100. Does this make sense to you? Yes.
Question about the principle of transferability. Does it have to be, like, when you extend it out 1%, does it have to be on that specific force? Like, for example, 300 newtons, does it have to be on that linear line?
Along its line, typically along its line of action. Right.
Okay.
So you can, one can also say, okay, hey, what about if I take this force and I transfer it somewhere here? That's not the same as the principle of transmissibility applied here, you see. So if I'm transmitting this force is going to be transmitted only along its line of action. And it makes no difference to me whether I'm drawing it here versus, whether I'm drawing it here, the moment caused is going to be the same. But it does not make sense for me to take this guy and then draw it out here. You see, the effect of the force itself has changed now, in that sense. Okay? So I can't do that. And even if I do that, it doesn't make a difference to me. Any questions before I proceed? Once again, this is statics, stuff from statics. So it is just a rehash of what we are doing. You have a couple of homework problems. You're going to have one more which resembles something like this. Okay? Is everybody following along? Okay, we'll move on then to find mz, moments about the z-axis. This is equal to 0, and all the moments about the positive z-axis are treated as positive, so it's typically my positive sign convention. I draw my line figure. X-axis, y-axis, and z-axis. Then I draw the moment mz, reaction moment. I immediately know that is pointing along the positive z direction, so I can throw it into the mix here. Then at the point B, I have all these forces that are sitting, so I draw them out. This is 200, 300, 400. Then I start eliminating one by one. Okay, so first of all, distances of 1 meter, 2 meter, not drawn to scale. And you can follow the same procedure for any kind of a 3D problem. You don't need to keep drawing the entire 3D figure every time. I did that the first time and the second time just to see, okay, these are all the rotations that are caused about that cross section. Typically nobody does that. Okay, the only thing you do is draw line sketches. Then I start whittling down the forces one by one. 400 newtons is parallel to the z-axis, does not cause a rotation about the z. If I take the line of action of the 300 Newton force and extend it, it intersects the z-axis. Right? So intersects the z-axis because, as I said, they are all lying on the same plane. They are lying on the same plane. Okay. So this is not going to cause any rotation about the z-axis as well. 200 Newton force. Perpendicular distance is known to me. That is the 200 Newton force. And if I use the right hand rule, fingers of my right hand aligned with the 200 Newton, my palm is facing the z-axis. I curl my fingers, my thumb is pointed along the negative z direction. Okay? So this is now going to cause times 2 meters. This distance here, if you want. Meters. So mz minus 200 times 2 is 0, or mz is plus 400 Newton meters. Okay, so I have all my moments, all my reaction forces, and I want to see if there are any questions so far. Yes. As I said, I'm doing it so that it makes it clear to everybody. If I did this in one single figure, it will look very cluttered. So it is your choice. If you feel that this helps you in understanding how these moments are produced, I suggest that you draw it. If you feel that you can get away with just drawing one figure where you show everything and then you do your calculation properly, it is completely your choice. Okay? As I said, you don't need to repeat each and every damn figure I draw on the board. Okay? Yes, sir.
So just to make sure, any forces that are either parallel to that specific axis you're taking the moment about, or that intersects its line of action will never cause a moment. So
Absolutely. I'll write that. I'm going to write that down. Bear with me for a minute. Push this fully up. I think that's now stuck. Huh? So maybe we do need to get back to the iPad. Huh? And push this up. Okay. So, if you have a force that is parallel to an axis, it will not cause a moment about that axis. No moment about that axis due to that force. Okay, Okay, not due to every other force. If I have a force whose line of action intersects an axis, same story. Then you're not going to have a moment about that axis due to that force. About that axis. And as an engineer, you have to estimate, okay, what are all the figures that are necessary for me to convey what I know about this problem to a person who has not seen this before. And that is what my thought process is okay, you may not have seen this problem before, but I just solved it in the morning. I could come and show everything in one single figure, which will make it really cluttered. But I want to show my thought process, okay, this is how I calculated the moments for each and every axis. And so which is why I'm drawing all these figures. And when you're solving problems, it depends on your perspective as to what you want to do. Okay? As long as you convey to me your thought process, and as long as I see that it is clear and uncluttered, we are good to go. Alright, any other questions on what we've done so far? Is everything clear in terms of force and moment balances? Okay. Since we have computed everything at the cross section at A, that is where the point A is residing, I'm now going to draw the circular cross section, and I'm going to list out all these forces and moments that are acting on it. If there is a force or a moment that I figured out to be negative, I'm going to reverse its direction when I draw the cross section. Okay? So this is now the cross section at the point